Okay, whoa, sorry about that. Okay, let's get started. And Katherine Scott is going to tell us about analyzing satellite imagery with Python. Thank you, Katherine.
Hi, guys. Okay, sound works. Cool. So my talk is called Python from Space, Analyzing Open Satellite Imagery Using Python, or using the Python ecosystem. I'm the image analytics tech lead at a company called Planet. I don't know if you guys have heard of us. We have a bunch of satellites. So I'm going to teach you how to use satellite data. So quick overview. This is a play in 3 parts. I've designed this, so we do fancier stuff at Planet, but this is at a software carpentry level of capability. And so this talk is actually meant for all of you to go out and do something with this stuff right away. So the user persona I used when I put this together was basically someone who's sitting, like wants to go to a city council meeting, has some problem they want to solve, and they need satellite data to go prove a point and do some good in the world. So I'm here if you have any questions afterwards, or Dana, who's right here up front, is also here, and she can help you. And all of this will be open source and up on the web as soon as I'm done and push the button. So you can go check it out, you can go play with it as soon as you're done. So we're going to go over 3 examples. We're going to go over how to get a bunch of space images and make a timelapse GIF out of them. And this is useful for showing change on the surface of the Earth. We're going to use OpenStreetMaps to get some data about the Earth and then use it to do some processing. And then we're going to create a quick little video using some satellite data. Okay, so why should you care about satellite imagery? And I think the biggest reason is we now live in this like post-truth world. And I'm going to use literally correctly here. Satellite imagery is literally ground truth about what's happening on the planet. So I'm going to go super like, I don't know if you've seen this movie, Koyaanisqatsi. It's going to be like that for a second. So this is Peru. This is eastern Peru. And that may look normal to you. What's actually going on is that is an artisanal, and not artisanal in the Portland sense, but an artisanal gold mine. And what they do is they take high-power hoses and they hose down the banks of that river, and then they use mercury and stuff to slurp up the gold. This is how it grows. That's like a couple months. This is what's going on in the Amazon. So this is in Bolivia. This is, I believe it's a sugarcane plantation. And this, again, is what happens over a course of a couple months. This is all primordial, like old-growth rainforest. That's what's going on. And that's like an area the size of downtown Portland. So this is a disputed island in the South China Sea. And I'm not going to get into the politics of the South China Sea. But what I can tell you definitively, science-wise, is that that building is causing degradation of the reef environment around it. And I don't think that's cool. Here's another facility. This is a purported nuclear research facility in North Korea. I don't like nukes. I don't think anyone should have them. I think we should all be watching what people are doing with them. Who's from California here? Remember, it didn't rain for like a year? So this is the Oroville Dam. And you can see up there on the top right, it's basically the water level is super duper duper low. This was at the height of the drought in like September, October. This is when the snowfall actually started melting, and this is when the Oroville Dam started the spillway started to degrade. So this actually caused downriver flooding and took out a bunch of homes and a bunch of farms. And when this kind of stuff happens, you need resources to actually go and get data to people out there so they can do search and rescue response. And just to make things end on a happy note, this is just the coast of Italy. So, sometimes it's just cool to go look at pretty stuff, right? All right, so let's talk about what's out there. So space is like this public-private thing going on. So our governments, European governments, a bunch of governments go and put up all these like super dope satellites. So there's a couple on top there, Landsat 8, Landsat 7, Sentinel. And since we're sort of transitioning to private partnerships, Planet actually has a bunch of satellites. We have our own flock of doves. There's like 140 something up right now. We just acquired the SkySats from Terabell and Google, and we also have a constellation called Rapid Eye. So we have a bunch of different little satellites that are commercial satellites. So here's something about all this stuff. All those guys on top, they're free. You can get that data whenever you want, wherever you want. It's not the prettiest API, but you can get it. And all the ones on the bottom, you can get some of that data for non-commercial purposes. So you can go and actually use that data to do whatever you need to do. So where do I get this public data? So USGS has an Earth Explorer. It has all the Landsat data for the past 40 years. There's also AWS has put up a bunch of that data from Sentinel and MODIS and a couple others. Planet has a bunch of resources for getting this stuff. We have Planet Explorer Beta, which means you can go and see everything that we pull down. There's also our Open California dataset. You can get anything in California. We give away anything for emergency response. We have an ambassadors program. So anybody who works for a nonprofit or an educational organization, you can get a limited amount of free satellite data. And then some of that Amazon stuff, I actually just put out a giant 100,000 image data set of all that deforestation and degradation in the Amazon. So if you do machine learning, come talk to me. There's data out there to help find that stuff. And finally, some of the other commercial satellite companies put out data, so Digital Globe and a few others do the same, especially for disaster response. All right, so let's talk about what satellite data looks like. So you think like, oh, satellites, they're just like flying cameras. Well, they're kind of like flying fancy science cameras. So our eyes see in 3 colors, right? They see in red, green, and blue. But satellites actually see in a much wider array of colors. So like Landsat sees basically shorter wave or higher wavelengths. So you go and you can see into the long wave infrared, and you can see into all these different colors that are on the spectrum that humans can't see. And what that means is that you actually can see stuff like when you look at this data, clouds and snow will look like different colors. Different kinds of crops will actually have different coloring based on what bands you're using. And it's really helpful. And what I've done is I've sort of superimposed our visual spectrum down onto the standard Landsat and Sentinel data. So you can see there's a wide bit more data that you're getting. So what this really means in practical terms is satellites aren't just cameras. They're like X-ray vision onto the planet where you can go and learn some cool stuff. A couple bits more about satellite data and some terminology. There's this notion of cadence, which is how often a satellite will go visit an area. For the big governmental ones, it's usually about monthly. And then for a lot of the planet stuff, it's either daily or monthly, or we actually have ones now that are tasked, so we can drive them to where things are happening. There's GSD, which is basically how many meters are in a given pixel of satellite data. So for the big guys that have all these bands, the resolution's a little bit lower, but you get all these bands. And then our stuff is a lot higher, but it comes every day too, so it's pretty useful. And then number of bands, as I've said before. There's also some satellite terminology that you should be aware of. Usually when you want to go look for algorithms for satellite imaging, it's called remote sensing, and that's the fancy name for satellite imaging. So if you Google remote sensing, blah, 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 you might get better results. There's orthorectification, which is the process of lining up our satellite data with stuff on the ground. So what you do is you don't always know where the image is on the ground right away, so you go and you do this algorithm, and you just go and you line it up with the ground map. There's nadir angle, which is the normal pointing of the satellite towards the Earth. And if you want to see something really cool, look up off-nadir satellite imagery. It's the coolest thing. There's raster and vector. So in the sort of remote sensing space, you'll hear people talk about rasters, which are just pixel images. And then you'll hear people talk about vectors, which are sort of outlines. That would be the border of a state. And a couple other more terms, UTM, which is Universal Transverse Mercator. It's just a coordinate system like Latin long. It's a little bit easier. UDM, which is Usable Data Map. It's basically a mass that shows you where clouds are and stuff like that. And then DAM, which is a Digital Elevation Map. And that just means if you have Latin long and you want altitude, the DAM will give you the altitude. And just to reiterate, raster means pixels. Okay, so I'm yapping. This is just a presentation. Who wants to write code? Let's write some code. All right, so I have 3 Jupyter notebooks. We're going to go through them really, really quick. The first one here, I'm calling the basics. And so if I gloss over this, remember that you can go and look at this as soon as you get home. So what I'm going to do in this Jupyter notebook is I'm just going to basically set up a standard sort of data science stack, right? So I'm going to have NumPy and SciPy and Matplotlib. And then I'm going to pull in a couple of different libraries that are very relevant to doing satellite processing. So I'm going to pull in Rasterio, Shapely, which is a geometry library. And then I'm going to pull in this package for IPython called IPyLeaflet, which allows us to build these super slick slippy maps and figure out where we are on the Earth and what we're doing. And then I'm also going to pull in some API keys and the Planet client. So my first step here is I just need to query what sort of satellite data I can get for a given point in the Earth. And we're going to use the Planet API to do this. Now, The way you query the Planet API is you give it this thing called GeoJSON, which is just like a geo version of JSON. You just put a bunch of Latin long in there in points or in a square, and you can get that point on the Earth. And to get that GeoJSON, I'm going to pop up a Slippy map and draw on it. So I don't have to think about like, oh, Portland's at, blah, 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 latitude, blah, 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 longitude. I'll just draw what I want. And then we can use that to start querying. So what I'm going to do here is I'm going to pull up a Planet Quarterly mosaic and set my API key. And I'm just going to create this map object with, and point it to my tile server and set some zoom, and then set a couple coloring parameters. And then realistically, the big meaty thing that's happening here is I'm putting in a draw handler. So as soon as I draw, I'm just going to drop that drawn object into a dictionary. And so then I can go look at the dictionary and look at the things I've drawn on my map. So I'll just do this. It helps if you load everything. There we go. All right, so I have a Slippy map. Sweet. So this is a real Slippy map. It was made in the past quarter. And it is the entirety of the world. And you can go and zoom around and look in here. And so what we're going to do is we're going to select an area of Portland that we want to build this animated GIF for. And I'm going to zoom right here where PyCon is. And so now we're going to query like I said, we're going to query the Planet API. And what we're going to do is we're going to say, take my geometry object. I want everything since 2013, which is basically everything since 2013 that is in the Planet system. I want it with cloud cover less than 50%. And then I'm looking for PSC 3-band. So that means just color imagery from the small planet scopes. You could query MODIS, you could query Landsat. All of those are available. Right now we're just going to do 3-meter imaging from the planet scopes. And then what I'm going to do is I'm going to take that query and I'm just going to dump it into a pandas data frame and print the data frame. And that will allow me to manipulate stuff and get stuff done quickly. So I'm going to do that. And ta-da, I got data. All right, and so what I can see here is a bunch of satellite data, when it was acquired, the geometry of the footprint, that is to say where on Earth it overlaid, the GSD, what instrument took it, that sort of thing. There's also some thumbnails, and that should be about it. Oh, the sun elevation, that sort of stuff, if you need that. All right, so that data was pretty useful, but we still need to clean it up. So what that query doesn't tell us is how much each individual scene actually overlaps with our AOI. So what I'm going to do is I'm going to pull in the Shapely library, and I'm going to take the footprints of all the images in that query, and I'm going to make them into shapes. And then I'm going to take my area of interest, and I'm going to make that into a shape. I'm going to calculate the overlap of those two shapes, so I know precisely how much of each scene is in my little area of Portland. And then I'm also going to go in here and add a couple other series where I just like clean up the datetime parameters because they're strings, and we want to set the datetime. So, whoop. Cool. So now what we can do is we can just use this Panda data frame to filter out to get the scenes that I want. And I can just do the standard pandas filtering. So what I'm going to do here is I'm going to actually filter out. I'm going to make 2 sets of data, basically. I'm going to make a set of data that is the cloud cover, where cloud cover is less than 10%. And all the scenes are before the first of the year. And they overlap my area of interest by at least 30%. And then I'm going to make a second bigger set that's everything since 2014, where the overlap is greater than 60%, and the cloud cover is less than 50%. So I go and construct those queries, and you can see I have 2 new data frames. One of them has 6 scenes. And the other one is going to have 15. And now what I can do is I can go overlay these on my original Slippy map so I can see what kind of data I'm going to pull down. All right. So I've basically taken the footprint of those and dropped them onto my map. And so now I can see the overlap of the first 6 scenes. And you can see most of them are pretty decent overlaps, not all of them. What we can also do is there's a thumbnail link in the API, so we can use that thumbnail link to go and see roughly what these things are going to look like. And they look like this. So you can see here's downtown Portland right here. I know it's tiny. Here's another one. Okay, and so this data looks good. So to get our data, it's actually requires a little bit of work. So these satellite images are uncompressed, full resolution super awesome, super deep data. And Planet doesn't actually store all of them ready to go. What you have to do is you have to kind of activate them. So we'll pre-process them, get them ready for you, and then after you activate them, you download them. And most of this is taken care of in the Planet API, but you have to be aware of a few things. So you have to know like the asset type, so what kind of satellite you want. So you can either go for like the big governmental satellites like Sentinel, or you can look for just PlanetScope, and then you need to know what kind of product you want. There's 3 kinds of products. There is an analytic product, which won't look right, but is useful for doing actual data science. There's a visual product, which looks pretty and is useful for doing visual stuff like we're going to be doing today. And then there's basically a UDM, which is usable data mask, like tell me where the clouds are. So what I've done here is I just went and put a little wrap around that to sort of make it easier to think about how I'm working here. So I have a function here that's called getProduct, and all it does is it tells a client to go get a particular scene that's that we've looked up. Another one to go and say activate the product, which is to say, hey, do all this pre-processing for me. And finally, another one to download. And finally, one to check to see if all my scenes are ready to go. So I'll load that in. And what I can do now is I can just write a really quick little method to say, hey, take my pandas data frame, give me the IDs of all the scenes that I want to get, and activate and download them as visual products. So I'm going to go and activate these. And that should be 6. And so I went ahead and pre-downloaded these because it would have been about like 300 megs and it would have taken a little while. So we've activated them, we've downloaded them, we have satellite imagery. We can look at it. So what I've done here is I've basically put together a couple methods just to load load these images up. And so these are geotiffs. And geotiffs is this sort of raster format that includes all of the information that you need to properly map and display these images, and a bunch of the sort of science data that goes with them. And so there's a lot of ways to go and open these images. You can use OpenCV, you can use GDAL, you can use skimage. Here I'm going to use Rasterio, but that's just one example. There's a ton of ways to do this. So I'm going to create these load image files. And then what I can do is I can just open up my images and bring them up in Matplotlib. This takes a second. Cool. Hey, so check it out. We got Portland. We are, I don't know if you guys know where we are. We are actually right here, right now. And this image is from the 10th, so just a week ago. Okay, so now we get images. One of the standard things that you want to do is just plot a histogram so you know kind of what your color distribution is. This is also for helpful for figuring out what percentage of clouds are in that image and that sort of thing. So again, it's just some basic NumPy and Matplotlib, and you can go and actually plot your histograms. So I've done that here. We can take a look at the histograms for these images. And we can see for that second image, seems really clear, pretty good. All this black over here, right, this is all zeros, so this is all black pixels. That's just this edge effect right here, because the images are rotated, so this is north. And then this little bump of white is either because of the rooftops or of clouds. And if something's really cloudy, you'll see a big bump over here. Another thing you'll want to do, and you'll want to do this especially if you're working with analytic products that have multiple bands, is you'll want to decompose and recompose your images into like simulated RGB with different bands. And so I just put together a really quick sample here of how to decompose the image into each of the channels. And all that is just doing your slice notation. And so you just take like one slice. So you can actually see right here, like we're taking the slice one by one. So that would be the red channel, or actually that's probably the blue channel, and this is probably the green channel, and this is the red channel, and for a 4-band image, this would be the NIR channel. So let's go ahead and plot one of these guys. Cool. So we can see here, they all look the same, but there's red, green, and blue all the way across. So this is just the red component of that image. All right, so all these images are really big, and we're not actually looking at downtown Portland like we wanted to. So we sort of cropped out this little area and said, we want to look at this, but the scene is huge. So we need to get that scene down to what we actually need. So what I've done here is I'll take my AOI and I'll dump it to a GeoJSON file. And I'm going to use a tool called GDAL, which is the Geospatial Data Abstraction Library. It's a C++ library. Runs pretty well on Linux. So there's some, you can either use it as a command line tool or you can use Python bindings. I'm going to use the command line for a lot of this, but you can just as easily use the Python bindings. And so what I'm going to do is I'm going to ask GDAL, and it's a really great tool, to take that input GeoJSON file and take my scene and then crop my scene down to that GeoJSON file. And I'm going to do that for all of my images. And I'm going to go put them into another file called crop. So we have our input images, and now we have our output images that are cropped out to the area that we wanted to see. And it's going to look like this. So I go run this. I'm just calling out to the command line using subprocess. And then I'm going to go and grab those images that I just created and then load them up using matplotlib again. So this looks pretty good. You'll notice one thing here, though, that most of these scenes don't actually overlap where we're interested in. This one does, but the rest don't. So what we're going to have to do is we're going to have to mosaic a couple of these scenes together to get a nice, good coverage of the area we're interested in. And what you can do is you can just basically feed a couple of these images to GDAL, and GDAL will compose them and then do the cropping for you. So let's just go and do that. So basically, this is the same command again, using the same parameters. But instead of just passing it one image, I'm passing it a couple images. And you'll see this again in a couple of the later examples. So I run that. And what we'll get is a nice composed image. And maybe you can see it. There should be a couple sort of stitch lines where you can see that these images were composed together. OK, so we've covered how to get a bunch of images, how to find a bunch of images, filter them, crop them down to what we want, and process them. So I'm going to pull it all together. So you remember at the beginning, I basically created two sort of sub-data frames, one with like just data from 2017, and then one from like 2015 onward. So what I'm going to do is I'm going to take that 2015 one, onward one. I'm going to grab all of the scenes from 2015 to now, and then I'm going to crop them all out, and then we're going to squeeze them together into an animated GIF. So this is just going to rehash the same code that we just wrote. All right, so what we're going to do is we're going to activate and download all those. And so while these are activating and download, I'll show you guys what we're going to do. So this is the same thing. We're just creating our clipped files, piping them to GDAL to cut out our AOI. And then for each of the clips, we're just going to use another command line tool called ImageMagick, and we're going to convert them to GIFs. And finally, we're going to use a final ImageMagick tool to do a convert operation, which will smash all those GIFs together into one big animated GIF. Cool. And everything's ready to go. So here's GDAL cutting everything down into our little AOI. And we're done. So this isn't the most recent one. Oops. Well, I'm already loaded, so let's just do this. So this is the output. And what's kind of cool about this is because we use the PlanetScope data, and we've gone through this process of iterating on satellites, what you can see is that the satellite quality improves over time. So these are probably some of the more recent ones. And then you can see some of the earlier ones probably aren't as sharp. And so you can actually see how the product is improved over time. OK, so second example. Who here has heard of OpenStreetMaps? All right, so I'm pulling in, so this is exact same examples, exact same set of code. And what we're going to do is we're going to pull in the OSM API. And then we're also going to pull in from GeoPy a feature called Nominatum, which is called a reverse geocoder. But otherwise, it's all going to be the same. And so I'm going to blow through a couple first lines of this notebook and just get to the meat of things. So what we're going to do, I should tell you what our objective is. So our objective here is we're going to go and query OSM to get all of the parks in Portland, right? And what we're going to do is we're going to download the most recent satellite data about these parks, and we're going to calculate the greenest park in Portland so we can go there when we skip out early on Sunday and we want to go have fun. So, and I'll show you guys how to do that. So we're going to activate our APIs. We're going to bring up our Slippy map. We're going to select a nice little area of Portland. we're going to do our filtering. And this is the last similar filtering. I've just sort of filtered out a lot of the clouds. And then I'm going to plot what we got on top. And we can see we have a nice bit of coverage on Portland. So we're going to take all these scenes and we're going to mosaic them together. Or we're going to activate them, download them, and mosaic them together. Okay, and so while that's downloading, I'm gonna start walking through the next little example here. So one of the most common problems I've heard with people getting started with this data is, I have this pixel, now I want to know where it is in the world and what's there. Like, I've found this thing that I'm interested in, how do we look that up? And the short of it is that we look that up by using OpenStreetMaps, and we get to OpenStreetMaps from going from pixels to this thing called UTM, Universal Transverse Mercator, to lat long out. Then we can do our query, and then we can map it back to our pixel. So I'm going to show you how to do that really quick. And I should mention here that OpenStreetMaps is totally free to use, and they're generally pretty awesome. But the interfaces are kind of cryptic. And so what we're going to do here is we're going to actually use GDAL again to open our file and get what's called the geotransform and the projection reference out of our geotiffs. So what I'm doing here is I'm using GDAL, I'm opening it up, I'm taking the projection reference object and just shoving it into a variable. I'm also taking the raw data and shoving it into a variable, and then I'm also taking the transform and shoving it into a variable. And then I'm just going through that first reference and finding out what UTM zone we're in, because we need that UTM zone to figure out, to calculate our lat long. So I do that. And here I'll see that all these images are in UTM zone 10N. So what we'll do is we'll write a really, really quick function here to convert pixel position to UTM. And we do that by getting, basically using that transform object that GDAL gives us, this transform right here. And it's basically just an affine transform, which is a fancy word for there's some math in there, but it's all pluses and multiplication. And so I've defined that function right here, and then I've also made a really quick draw point function. And so what we should be able to do now is we should be able to take a random point on our scene, open our file, get that pixel in UTM, convert that UTM to lat long, and then to query, create this nominatum object, and basically query what's on that point in the Earth, and we can display it. So let's go ahead and do this little chunk here. Oops. This should return. And so whatever this pixel is right here, this position that I defined, 3,000, 1,400, is 7935 North Choctaw Boulevard, Kenton, Portland, blah, 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 blah. So for completeness, we should plot this and actually make sure this makes sense. I'm going to need a Portland native here to confirm that this is roughly correct. Oh, it's a different scene. Well, this one is super cloudy. So I did. It is correct. All right, I did this yesterday. This is all clear. All right. I did this a minute ago. It was all clear. So anyway, so working with OSM is super hard. Like I said before, the interfaces are kind of cryptic. I love the data to death, but they're a pain to work with. So the way I like to work with it is actually using this Overpass Turbo API. And what this is you can basically write this sort of cryptic query in here, and Overpass will basically go and find stuff for you, just like Google Maps would. So I constructed a query here to find all the parks in Portland. And I've already run this. It takes like a couple minutes, but you can see that it's actually defined all these parks. I know there's this big one here. I think this one might be one of the closest big ones to us. There's this cool circle. But anyway, what you can do is you can actually export this data as GeoJSON, which means you can work with it in our Slippy map. We can use it to crop stuff out, which means we can do analysis with it. So I've already saved that into the notebook, and there's an example. And so what we're going to do is we're going to use GeoPandas, which is just like a little syntactic sugar on top of pandas, to load up this GeoJSON file. And we're going to go through that GeoJSON file and just look at the size of the different parks that are in Portland. So let's do that. All right, so we've loaded the GeoJSON file that we've gotten from OpenStreetMaps. And I'm just printing the head here so we can see what's in here. Most of it's empty. But there's actually some cool stuff in here. I commented this out, but you can actually, if there is in OpenStreetMaps, there's actually Wikipedia data. So like it'll return that, which is pretty cool. And so what I'm going to do now is I'm going to take that data that we just got, and I'm going to go put it in our local map so we can see what's up. Okay, so I pulled this down from Overpass Turbo, and now I can see in my map where all these areas are overlapping. You guys can see that? We can also do this so you can see it a little bit better. There we go. Okay, so now we got that. What we want to do is we actually want to start analyzing these parks for interesting data. So the first step in analyzing these parks is that we need to go and get all the parks. So some of these things can be chunked out into multiple bits. You have these parks where it's like one corner over here and one corner over here. So what we're going to have to do is we're going to have to group these parks together real quick, and I'm going to group them together by name, which is really great. This is what like GeoPandas is made for. So we're just going to run this really quick command, and I'm also going to have it print out the size of each of these parks, just so we can see what we're dealing with. Okay, so now I'm going to write two quick functions. The first one is just going to pull a smaller chunk of GeoJSON out of that big GeoJSON file that we got, because it's basically just a dictionary. And then I'm going to take that GDAL command that we wrote before, and I'm just basically going to take my scene, and I'm going to apply that command to my image. So you can see that here. We're just basically going through this GeoJSON object and writing out to file. And then this is just the same sort of GeoJSON GDAL command, where we go through and crop our scene out. So I'm going to go ahead and run this. If I do this first. And it's just going to cook through really, really quickly. And GDAL's going to crop all these guys out for me. And now I want to go and actually see what these guys look like. So I'm going to make this a little bit easier on my notebook. This is just a quick hack that I think everyone should be aware of. Instead of working with the TIFF files directly, I'm going to use a tool in Imagery, which is like one of the best libraries ever, to convert my TIFF files into JPEGs. And then we can visualize them a lot easier. So I'm going to run that. And what we end up getting is something like this. So we get all these nice little crop files of our parks. And these are really nice and easy to work with. All right, so this is where you guys would probably want to start inserting your code if you want to do analysis. So what I'm going to do here is I've written this sort of not so great function called calculate greenness. And all this does is it looks at every single pixel in the image and takes the average of the red and green, or the red and blue channels, and looks at how much greener the green channel is over the red and blue channel. And then what I do is I calculate the number of just colored pixels in total, and I get an average greenness over the other two channels for every park. So this is a like rough proxy measurement for like how green the parks are. So I go and can write this function, and then I have a little listcomp branch in here where I can go and take each of my input image, or all those cropped images that I made, and run this function over it and save the results. And so there, we've just calculated the greenness for every park in Portland. And now what I can do is I can just go and plot all this data. And here we go. This is the greenness of the different parks in Portland, all set up, really easy to do. And right now, Lillis Albania Park is ahead. Let's see if this actually works. So what I'm going to do is I'm going to re-display all my images, but this time I'm just going to do it in the sorted order of greenness. Let's see here. Oops. Looks pretty green. Looks pretty green. Yeah, it's super exciting, right? Woo! All right, wait. So what we can do is we can also plot this on our map too. So like we can actually put this up on the web and just have our daily update of what is super green in Portland today, right? Which seems like something that should be happening in Portland. Cool, and I am totally on time. So I have one last demo to show you guys. And this one is super fun because I think this one is super powerful. Like YouTube sort of dominates our lives anymore, and satellite images are nice, but sometimes you get this high-res satellite image, and you really want to be able to focus on little things, or you want to draw attention. So I wanted to make a demo of where we can actually do these super cool flyovers of all this satellite data. And I think this is really useful for stuff like if you want to go talk about a river ecosystem or a pipeline, or sort of show relative position of, say, one smaller city that's having issues with respect to a bigger city that people might have heard of. So what I'm going to do is this is exact same setup as before. Exact same little map. And now what I'm going to do is I'm going to not just select an AOI. Actually, I'm going to do that over again, so it doesn't take forever. I'm going to select a little AOI, and then I'm going to draw a path. And this is the we're going to basically make a movie that is flying over this area. So why don't we come down the river here? We'll go here. We'll go here. We'll go up here, up here, up here. We'll go past where we are right now. Maybe stop right there. All right, so I've defined a path, and I've defined an AOI. Same query. Cool. And again, we'll just plot what we got. And this is the exact same boilerplate code. There's nothing up my sleeve. There's nothing fancy going on. You see we get a bunch of overlapping scenes that look pretty good. We're going to activate and download those scenes. You see, I said go get coffee here. I would kill for a cup of coffee right now. And so what we're going to do is, you can see, and I'll skip ahead here while this is going on. What we're going to do is we're actually going to go take all these scenes and we're going to make them into a big mosaic, which is going to be our area. And the way this is all going to work is that we're going to take this big, huge, giant image that we made, and we're going to build a little sub-window, and we're going to move the sub-window between all the points. So we have to like take our points that we defined, and we have to interpolate between them. So that looks good. Let's go and download all these. And they're all ready. So now I'm going to use GDAL again, same thing. I'm just going to go make this GDAL call and pass in all of the scenes that I've found. And this will take a second because this is going to be a big, huge image, which is kind of cool. It's going to be a huge chunk of Portland. And then we're just going to go visualize the output. Takes for a second. Cool. And it's so big it even takes a second to load. So this is, should we gaze for a second on how beautiful Portland is today? Look at that. Okay, so now, like I said, all we need to do is move this crop window around this big, huge image, and we have a bunch of little images that we can then stitch together into a video. So I'm going to define a quick crop function, and I'm going to make this easy on myself. So I'm going to define this crop function. Usually you do crop functions like top, left, and width and height. This one's going to be based on the center and then the width and the height. So I'm going to define a crop function, and I'm going to quick test that it works. And it crops. Cool. Unit tests in code. All right. So there's one little trick that we have to figure out to make this work. And that is to say that the points that I put in the Slippy map above, those are all lat longs. And we need to get those in pixel values, which is sort of the reverse of the problem we just solved. And again, we're going to use GDAL to get that geotransform. And then we're going to take that geotransform. Oh, how does this work? We're going to take that geotransform. We're going to transform our points, or transfer the corners of our image to get them as lat long. And then we're going to take those lat longs and we're going to like linearize the entire image. I know that sounds fancy. It's really not. We're just going to say if we have a lat over here and another lat over here, we're going to subtract the difference so we know that it goes from here to here. And we'll map each of those latitudes in between to pixels. That's all this function is going to do. So the first thing we're going to do is we're going to define this function called getExtends. And this just returns the corners, a list of corners in the image in a normal format. And these are all, I think, going to be in UTM. And so it just takes the corners and appends them to array. And then we're going to build this other function here called reproject coordinates. And what this does is this basically is calling out to GDAL to get the transform again. And it transforms each of those points from, I believe, U2N to lat long. And so now we're just going to call it. We're going to call these two functions that we wrote and reproject, and we can get the, oops. I will do this at least one more time. So here, for this big image that we wrote, this is the Latin long coordinates of the output of the corners of that image. So now all we have to do is map each of those lat long positions to the pixel positions inside of our image, and we can start cropping our image out and building our movie. So this is, like I said, I call this poor man's lat long. It's a bit of a hack, but it works pretty well. We're just going to linearize the points. And all we're doing is we just get the points in our image. Like I said, we have one point over here. We have another point. You're just mapping two numbers together. So we're going to define that. And we're going to draw it, just to check our work again. So we've just taken, what we've done here is we've just taken those points that we've defined on that Slippy map, translated them from lat long, and got them into the pixel positions on this image, which is pretty cool. So now here's basically the last step. We have points in space, right? And we need to basically chart a nice smooth path in between those points in space to make our flyover movie. So what we're going to do is we're going to write an interpolation function. And if you guys have never done this, it's super fun. All you do is you have like multiple points on a line, and then you take your first point and your second point, and you say, make a nice even bit of number of spaces in between. Give me all the x, y values in between. And you can get super fancy with this. You can do like splines and headings and change this around, but we're going to keep this really simple because right now we're just trying to introduce our audience to this. And then I'm just going to make another function here, which is called build scenes. And what this will do is it'll just basically take our big image, our crop window, do some tests, and then resize things down, and then save it to a numbered file, a sequential numbered file. So I'm going to define these functions. And I'm going to test all this stuff in my Jupyter notebook before I even run it. So what we should see here is if all our points go around, we're about ready to go. Looks about right, right? So this is what we're going to crop out. All right, so here's the big finish. We're going to actually go and run this. It'll take a second. Now, I've said we're going to build a movie with that resolution of 640 by 480, and we're going to load the image. Let's take a second. Now, I was going to do this from command line. What we're going to use to actually stitch this movie together, we're going to use a command line tool called AVCom. It's kind of like FFmpeg. It's a pretty handy tool. If you've never done this before, it's a really clever tool for making movies, where you can just generate a bunch of images and then splice them all together. So this is finished. And what I can do, I'm just going to copy this command line. I'm going to paste this in here. And this is going to cook. And we're going to open this up with our friend VLC. And here we go. Ooh. We have a flyover of Portland. And since this is a notebook, right, guys? So these are notebooks. And these are all open source, and I've shown you guys where to get all this data, and how to use it. And so I really hope that you all can go out and actually take this stuff and put it to good use. Go find something in your home, like where you come from, and figure out how satellite imagery can actually help you solve a problem, because it's really powerful stuff. All right, thank you guys.